This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics. And in this lecture, we're going to be talking about relative motion in 2 dimensions. So when we talk about relative motion, we've talked about it before. If you'll remember our bullet example, the movie, and the math is going to be exactly the same. Now, we're going to restructure the math just a little bit to help us set us up for fixed or rigid body kinematics. And so that'll be good. So just be aware of that. But the math is the same. The real difference now is that we're going to be working in 2 dimensions. And so if we're working in 2 dimensions, our best bet is to do vector addition in the Cartesian coordinate system. So it's possible that we've worked some set of kinematic relationships in a different coordinate system. We're all for that. That's great. But what we're going to then want to do is convert that from whatever, either the path polar or Cartesian, into Cartesian, a common Cartesian system with a common origin, so that we can do vector addition to calculate the overall position. And so position, velocity, and acceleration. So let's think about position first. So let's say that we wanted to know where position B was, RB. And if we're thinking about what RB is graphically, on my chart here, move B just a little bit, this would be the position of B. But let's say we didn't know that. Let's say instead we knew where A was, and we knew something about B with respect to A. So there's the position of A. And remember, when we say the position of B with respect to A, we're going to write it this way. RB with respect to A. And our arrowhead's going to go at our point of interest up here at B. And our with respect to is the new origin. So this is RB with respect to A, like so, with point A. If we wanted to get RB, what we do is we'd simply just say RA plus RB with respect to A. And you'll remember that we said that RB with respect to A was equal to RB minus RA. Well, mathematically, we could just shift that over, and that's exactly what we'd get. And so here's our position kinematic diagram and example for 2 points A and B. Now, this would have to be customized to whatever problem you're actually working. So that's the thing. Now, when we think about the velocity, we're going to do the same thing. And so if we wanted to know the velocity of point B, and we knew the velocity of point A, and we knew the relative velocity of B with respect to A, we could just add them up. So let's say that we knew that point A was going like so, and that related to, if we wanted to find the velocity of point B, we could do velocity at A plus B with respect to A. So let's say that that's this direction. Like so. And we could do the parallelogram, or we could just do tail to head. So plus velocity of B with respect to A is going to tell us that our overall velocity is like so. So again, it's just vector addition. We could do the same thing for our acceleration. The acceleration of B is equal to the acceleration of B of A plus the acceleration of B with respect to A. And so if we know the acceleration of A, we can do something like this. I'm going to erase my velocity. Well, actually, I'm just going to do a different one. If I've got my B down here, I might have something like the acceleration of A plus the acceleration of B with respect to A is going to give me the overall acceleration at A. And so sometimes we might, at B. So sometimes we might have to draw a separate diagram like that. But this is the basic idea of what we're looking at. We're just using that vector addition to add them up. Really not too bad. So what we would typically do is break each component into its x and y components, each either the position, velocity, or acceleration of A or B with respect to A, all of those into their i's and j's, add up the i's, add up the j's, get your final answer. And so our procedure for such a thing, this class of problems, is going to be exactly what it was before. We're going to start by drawing our kinematic property diagram, something a bit like that. And then once we've done that, we can write our relative motion equations. That would be these guys over here. And that would be in x and y. Remember, in Cartesian, in 2D, each Cartesian equation, because it has those I and j components, that's actually two separate equations. And then we could do the kinematic relationship equations for each point. And then hopefully we have enough equations in play that we can solve for any and all unknowns. I look forward to working an example problem with you in class. We'll see you then.